Welcome to third lecture on the topic retaining wall. I am Vaishak C, Assistant Professor, Civil Engineering Department, Engineering College, Jalawa. We already discussed about the introduction to all retaining wall, such as what are the types, what are different stability issues, what are the different design criteria and the proportioning rules. In this class, we are going to take a problem and I'll walk you through this problem in this lecture. So here is a design problem. The question is to design a cantilever retaining wall. The first thing I want you to do is to read the question carefully and note down all the given points. While reading the question, it is to be noted that you can see that the backfill is a horizontal surface, it is level, but we have an additional surcharge pressure of 40. The backfill height is given as 4 meters from the toe side, from the ground on the toe side. Now they have also given the foundation depth and the SPC value, and other details are also given, such as the unit weight of soil is 16 kN per meter cube and phi angle of shearing resistance is 30 degree. The coefficient of friction mu is also given as 0.5, and they have suggested to use M20 and Fe415 steel for design. One more thing to note here is that in this question the foundation depth is already given as 1.25. However, some questions the foundation depth will not be given. In that case, you will have to find out the minimum foundation depth according to the Rankins formula. It goes like this: the minimum depth of the foundation will be P by W into 1 minus sin phi by 1 plus sin phi the whole square, where P is the bearing capacity, W is the unit weight of the soil, and phi is the angle of repose of the soil. So in this question also, if you are trying to work out using this formula, the minimum depth comes equal to around 10 by 9, so it is almost equal to 1.1 something. Okay, that is the minimum depth, but in the question it's given it's the foundation depth is 1.25, so we are going to use the foundation depth as 1.25. Okay, this next thing is so first thing to do is note down all the given data and try to make a diagram from the given data. Okay, so the foundation depth is 1.25 in the toe side, so that is to be noted. From the base of the footing to the top of the ground level on the toe side is 1.25. Then the backfill height was given as 4 meters, that is already marked here, so this much is the backfill. Okay, and in addition to backfill there is an additional surcharge. So surcharge is nothing but an additional pressure over the backfill. Okay, so what we have to do here is, like, whenever a surcharge is given, we have to convert that into equivalent height of surcharge. Okay, so this means that we'll convert the pressure into an equivalent soil mass having a height of HS. Okay, so this can be said like the surcharge pressure will be same as the pressure exerted by the soil, HS into gamma E. So in this idea we can find out what is the value of HS, that is Ws by gamma E. So that is 2.5 meters. So we have an additional 2.5 meter height of soil also, which is to be considered as a surcharge height. Okay, so the total height of the soil is 7.75 meters. You can also find out the CA and CP values. It being the level surface, there is no requirement of beta. It is one direct formula: 1 minus sin phi by 1 plus sin phi and 1 plus sin phi by 1 minus sin phi. So CA and CP values are already known. The next step to do is to do the preliminary proportion. So for doing the preliminary proportion, we already know that the first thing we learned is the height of the thickness of the bottom slab or footing. So thickness of the footing is 8% of the total height, so we take 8%, 0.8 of total height H plus HS, so that comes about according to 0.62. so 0.62 is this height, then the Stem thickness has to be slightly more than that of the base slab thickness at the bottom. So we choose a value of 0.65 at the base, and the stem is tapering all the way up to 200 millimeters at the top. The next thing we have to do was to calculate the length of the heel, which is including the thickness of the stem, which was called as x. So there is a formula for x, Ca by root 3 into h plus hs. So x is about 2.58. So the length of the heel slab is 2.6 approximately, we will take it as, and the length of the total base will be 1.5 times x, which is 1.5 into 2.6, which is 3.9. So the total base length is 3.9. Okay. Next we will see the stability analysis using this preliminary dimensions. So first thing to see is we have to draw the active pressure diagram. So active pressure diagram, we already have a pressure due to surcharge of about 14 kilonewton per meter square at the top, which means that this pressure multiplied by Ca will give the horizontal pressure at this level. So that is Ca into Ws. So this is at the top pressure value, at top is Ca into Ws, and the pressure value at the bottom is Ca into Ws plus the pressure due to the additional height of the soil. So that is to be 404 meters plus 1.25 meters, which is 5.25 meters. So at the bottom the pressure will be an additional pressure of Ca into gamma E into H, where H is 5.25. So this is your pressure diagram. The pressure diagram can be broken down into two. It's a trapezoidal distribution. This can be broken down into a rectangular distribution and a triangular distribution. So the rectangular distribution would be having the total force acting at h by 2, and triangular force will be having a total force acting at h by 3 from the bottom. Okay, so we can find out PA as Ca into Ws into total height, and PA2 as the area of the triangle, half into Ca into gamma into H into H. So we have PA and P1 value, and also it acts as H by 3 and H by 2 respectively. Now you can calculate the moment due to PA1 and PA2, which is nothing but force into the lever arm. So this moment is nothing but overturning moment. It is moment at heel. So it is a anti-clockwise moment. So we get an anti-clockwise moment, overturning moment of 312.4 kilonewton meter. Now in order to stabilize this, we have a restoring moment caused by all the weight about the toe slip. So what we're going to do is we are going to divide the weights into different portions: W1, W2, W3 and W4. So we'll take a W1 as the total height of the soil starting from the surcharge top until the top of this slab, bottom slab. So this much height we are having soil, so the weight of that will be 16 is the unit weight into 2.4 is the length of this, width of this rectangle, and height of this is 7.75 minus 0.62. We have to subtract the base slab thickness. Another thing we are going to do is we are going to find out the moment about, in order to locate the total W and total location of total weight W, which is essentially distance of xw xw from the heel. So what we have to do is, it is static analysis actually. We have different forces acting at different centroids, so find out the total void distance. The resultant will be the w1 into x1 plus w2 into x2 plus w3 into x3 plus w4 into x4 whole divided by total w. So w1 is for the rectangle, w2 is for this small rectangle of the stem which is shaded in white and it's having a unit density of 25 kN per meter cube. W3 is actually this triangle which was already included in as SOL. So what we do is but in that place it is actually concrete. So we'll add the weight of the concrete and subtract the weight of the soil from there. And W4 is the weight of the base slab. And for each of these we locate the point at which this weight acts from the heel, that is distance from heel to each of the loads W1, W2, W3 and W4. So from these values we can calculate what is the location of the total vertical result force, xw mw by total w, that is 1.432. It means that total weight acts at a distance of 1.432 meter from the heel. So this weight is actually a restoring force or a restoring moment about toe. So restoring moment about toe is going to be w into this much distance, which is nothing but w into L minus xw. So we got the restoring moment also. Now calculate the overturning moment now calculate the factor of safety for overturning, which is 0.9 mm divided by mo. So it is 0.9 into 9050.3 divided by 1, it's 2.61, which is far greater than 1.4, and hence the given dimension is stable against overturning. Now we will see the soil pressure checks, that is we have to find out both Qmax and Qminimum is satisfiable or not. So in previous question we already found out that, in the previous slide we already found out that W is acting at a distance of xw from the heel, as well as R is acting at a distance of LR from heel. R is nothing but W. So the aim is to locate what is the value of LR. So if we take the moment about heel, both MO, which is the moment due to active pressure, and MR, which was the moment due to W, both are anti-clockwise, and the moment due to R will be clockwise. So in this case, if you want to equate the moment at heel to be 0, we get MW plus MO is equal to LR into R. So the value of LR is going to be 2.284. Now we have to find out what is called as eccentricity. Eccentricity is nothing but the distance from the center line to the reaction location. So in order to locate eccentricity, it is very simple, LR minus L by 2. So we get eccentricity value is 0.334, for which the check is it should be less than L by 6 value. L by 6 value is 0.65. It is less than L by 6 value, so it is okay. This indicates that if we divide the bottom slab into 3 equal portions, 1/3 portions, the resultant reactions lies within the middle 1/3 portion. Okay. With that, now we can calculate what is the Qmax and Qminimum value using the formula R by L and 1 plus 6E by L and R by L and 1 minus 6E by L. We get a Qmax value which is 142.4, which is less than 150 kN per meter square, which is SPC, and Qminimum value which is 45, which is greater than 0, which means that there is no tensile force acting at the bottom causing cracks on the footing. So we get a trapezoidal pressure distribution at the bottom, which is almost equal to a triangular distribution. Now we will see the sliding check. As we already know, the sliding force PA was PY1 plus PA2, which is 143.5, and the resisting force is nothing but mu into R. So reaction value was already found out as 366.8, which is nothing but the total weight W, and mu is 0.5 given the question. The value of F is 183.4 kN per meter. Now if we apply the sliding factor safety for sliding, we find that factor safety for sliding is 1.15, which is less than 1.4. So the sliding check is not satisfied. So in this case, what we are going to do is we are going to provide a shear key. The nominal shear key dimension is 300 millimeter by depth and 400 millimeter by width. It is usually provided below the stem so that the reinforcement from stem can continue all the way to the shear key. So we choose a distance of 1.6 meters by geometry only. Okay. So what the shear key does is it mobilizes a block of soil which is at an angle of 5 degrees from the corner of the shear key. So it mobilizes this much of soil, and this soil will exert a passive pressure on the wall which is moving towards it. So we have to find out the area of passive pressure diagram, which is actually this trapezium. So before doing that, let's find out what is the value of H2. So we already neglected an initial top height of 300 millimeter because it is a topsoil. Okay, so H2 is going to be this much height was 1250, 1.25 foundation depth minus 300 plus a shear key depth 300 plus 1.6 tan 30. So we got H2 as 2.17 and H1 as 1250 minus 300 950. So the area of the trapezium is nothing but the area of the triangle minus big triangle minus area of the small triangle. So we get PP value is 91.4. This PP will provide an additional force to the resisting force to F. So total resisting force now is F plus PP. Now if you calculate the factor safety against sliding, we get 0.9 into F plus PP whole divided by PA, and that is equal to 1.72. This 1.72 is greater than 1.4, hence the sliding check is satisfied here also. So what we see was the initial proportion chosen was satisfying all the stability conditions, overturning and soil pressure checks, but it was failing against the sliding check. But once we provide a shear key, and with the help of the partial pressure mobilized by shear key, we are able to overcome the sliding check also. So in this case, we accept all the initial proportion as the final proportion. In the next class, we'll continue with the design and detailing part of the same problem. Thank you.